When surveyors look through the lens of an optical level, they rely on a foundational premise. They assume the line of sight shooting out of the instrument is perfectly parallel to a flat, horizontal ground surface. But the Earth is a sphere. Over long distances, the physical ground physically drops away from that perfectly straight horizontal line of sight. This introduces the first systemic error in long-distance surveying. Because the ground is curving downward, objects positioned far away will sit lower relative to the instrument's straight horizontal line. Viewed through the lens, the reading on a distant leveling staff will be artificially high, making the ground appear lower than it actually is. This diagram shows the geometric divergence creating this error. Notice how the solid line of sight continues outward, while the dotted level line bends beneath it. To fix this, surveyors apply a mathematical curvature correction. C sub c equals negative 0.0785 times d squared. D is distance in kilometers. The value is strictly negative because the uncorrected reading is inflated by the Earth dropping away. We subtract this error to find true elevation. On a standard construction site spanning a few dozen meters, this curvature error is mathematically negligible. But when spanning a valley or river, this geometric divergence completely invalidates the raw elevation data. Curvature is only half the problem. As light travels over those same long distances, it encounters a second major environmental distortion, atmospheric refraction. The Earth's atmosphere is not uniform. It is a gradient of varying air densities. As the optical line of sight passes through these layers, the light physically bends downward toward the denser air near the surface. Perversely, this downward bending of light causes the target object to appear higher through the lens than it physically sits on the ground. Because refraction pushes the visual target up, the staff reading is artificially lowered. The correction factor is a positive adjustment. C sub r equals positive 0.0112 times d squared. Combining the negative curvature and positive refraction formulas gives the total correction. The simplified equation for environmental error is C equals negative 0.0673 times d squared. But this formula has a fatal flaw when applied to extreme geography. To solve it, you must have absolute knowledge of the exact distance, d. If you are standing on the edge of a wide, fast-moving river or an impassable canyon, physically pulling a measuring chain across the gap to find d is impossible. Without an exact distance, we cannot calculate the correction factor. We have to abandon the standard formulas entirely and find a geometric method that makes the environmental error mathematically irrelevant. This is where we introduce reciprocal leveling. It is a symmetrical surveying procedure designed specifically to bypass the unknown distance problem. The core logic relies on physical mirroring. By taking a pair of readings from one side of the obstacle and then crossing over to take a mirrored pair of readings from the exact opposite side, surveyors exploit this structural symmetry to perfectly cancel out the unknown variables hidden within the massive, impassable gap. To prove how this works algebraically, we first define a temporary mathematical variable, e. This letter represents the total combined error of curvature, refraction, and any imperfect instrument calibration over the gap. This diagram shows our setup at station A. We take a near staff reading, A1. Since distance is 0, error E is 0. Next, we read the distant staff at station B. Crossing the gap, this reading, B1, is corrected by unknown error E. To find the true elevation on the far bank, the pure mathematical reading must be the observed reading minus the error, that is, B1 minus E. We can now write our first algebraic equation. The true difference in elevation between the two banks, which we'll call D, is equal to the true far reading minus the true near reading. So D equals B1 minus E minus A1. We now have a working equation for the true elevation difference, but on its own it is entirely useless. We still have absolutely no way to solve for E. To solve the system, we pack up the instrument and physically relocate to the opposite bank, station B. Operationally, this shift must happen fast. If the atmospheric temperature and pressure change, the environmental refraction shifts completely. By moving fast, we ensure that our error variable, E, remains a constant value. At station B, we take a near reading, B2, with 0 error. Then, shooting back across the river to station A, we take distant reading A2, which is corrupted by error E. Our second equation becomes true difference, D, equals B2 minus A2 minus E. Looking at these notes, we add the equations from station A and B. Expanding them out, the negative and positive E variables perfectly neutralize to 0. Dividing by 2 reveals the final formula, D equals B1 minus A1 plus B2 minus A2 divided by 2. By mirroring their physical positioning, surveyors isolate true elevation natively, no measuring the span distance and no calculating atmospheric coefficients. To see how this derivation holds up in practice, we can run the math on a standard professional civil engineering exam problem. The parameters are straightforward. We need to find the true elevation difference between two separate riverbanks, identified as point P and point Q. Here is the raw field data collected from reciprocal leveling at the site. It is a simple grid showing instrument locations and corresponding staff readings. First, we extract the readings from the initial instrument setup on the near bank at point P. The near reading, A1, is 1.36 meters. The distant reading taken across the river, B1, is 1.96 meters. Next, we extract the readings from the second instrument setup, located on the far bank at point Q. Looking back across the water, our distant reading, A2, is 1.52 meters. The near reading at our feet, B2, is 2.02 meters. This simple grid of 4 uncorrected numbers contains all the geometric data required to entirely bypass the curvature of the Earth. We bring back our derived reciprocal leveling formula to process the raw data. We slot the 4 specific field values into their respective variables. The true difference equals 1.96 minus 1.36 plus 2.02 minus 1.52, all divided by 2. Calculating the first half of the numerator, which represents the uncorrected elevation difference from the perspective of point P, yields exactly 0.60. The second half of the numerator, the uncorrected elevation difference from the perspective of point Q, yields 0.50. We complete the arithmetic by averaging the two perspectives. 0.60 plus 0.50 is 1.10. Divided by 2, we get a true error-free elevation difference of exactly 0.55 meters. The exam problem provides one final given parameter. The known reduced level, or established elevation, of point P is exactly positive 60 meters above datum. To apply our 0.55 meter difference correctly, we now have to look at the physical orientation of the landscape. In our initial data, the staff reading at point Q was higher than the reading at point P. A higher staff reading means the optical laser had to travel further up the measuring stick, which physically means the ground at Q is lower than the ground at P. Because point Q is lower, we subtract our true difference from the known elevation of point P. 60 meters minus 0.55 meters gives us 59.45 meters. That is the exact final reduced level of point Q. Reciprocal leveling bypasses the physics of the Earth entirely. By imposing strict symmetrical geometry on the data collection process, surveyors ensure that massive, unavoidable distortions cancel themselves out, leaving only the pure data behind.